In this video, we want to talk about change of basis. So up to this point, we've been working with the standard basis vectors. So if we have a graph here, and we have the x-axis and the y-axis, we know that the x-axis is a perfectly horizontal axis that's marked off in increments of the standard basis vector I. So remember, we have the standard basis vector I, which is 1, 0. So every increment here is the vector 1, 0. We start at the origin and we move out toward the positive direction of the x-axis, one I, and then another I, and then another I, and then another I. So we've got this whole axis marked off in these increments of I because I is just the unit vector. It's 1 unit long, and so it moves out in the positive direction of the x-axis. Or if we take increments of negative I, we move out in the negative direction of the x-axis. We know that the y-axis is marked off in increments of j, which is the standard basis vector 0, 1. So we've marked off here every 1 unit, 1, 2, 3, 4. These are all units of j. So for example, if we wanted to plot the vector 5, 3, so let's say we have some vector v, and we'll call it 5, 3. We know already that we can express v as 5i plus 3j, because we have positive 5, positive 3, so that's positive 5i plus 3j. And if we want to sketch that, then we would start at the origin here, and we would go out 5i, so 1, 2, 3, 4, 5, and up to 3j, and so we would end up right here. That's 5 units of I out along the x-axis, and 3 units of j up along the y-axis. But the point we want to make now is that we can switch the basis for R2. So remember, this is R2 space, and basically we're saying that the vectors I and j form a basis for R2. So we've been defining R2 space in terms of the standard basis vectors. So if we call the basis of R2 B, let's say we've been defining it as B, we've been defining B in terms of the standard basis vectors I and j. But now maybe the point is that we want to use a different B. And the reason that we want to learn this is because changing our basis going forward is going to be something that'll help simplify lots of problems that we tackle in linear algebra. It's not always the most convenient to use the basis that you've been given just by default. Sometimes it makes the problem a lot easier if you can change the basis. So we want to understand now how to change the basis. So instead of having the basis B, which is defined by the vector 1, 0 and the vector 0, 1, let's say instead that we wanted to use two different vectors. Maybe we'll call them, let's say, the vector x and the vector w. We want to define our basis in terms of these two vectors. And let's maybe say that the vector x is the vector 2, 1, and the vector w is the vector 1, 1. The point is that the axes that we're used to using are defined in terms of I and j. So if we want to switch the basis to be defined in terms of x and w, we need a totally new set of axes. We need this x-axis here that's marked off in increments of this x vector, and we need the w-axis that's marked off in increments of the w vector. So if we sketch in the vector 2, 1, here's what that looks like. We would again start at the origin, and we go out to 2 and up to 1, and we get to this point right here. And so that would be our first vector x. If we mark off another increment of x, we keep going in the same direction, we get to this point right here. If we keep going again, we get to this point right here, and then again, we come out to here. And so you get the idea that we have these increments of this axis defined by the vector x. So I'll just go ahead and sketch in the rest of those. So what we're saying then is if the normal x-axis is 1, 2, 3, 4, etc., out toward the positive direction of the x-axis, this new axis that's defined in terms of the vector x, this is 1 increment right here, 2, 3, 4, because I'm marking it off in increments of this x vector. Same thing here with this w vector. It goes through the point 1, 1, so starting at the origin, we'll come out here to 1, 1, and then just keep going in either direction and mark off a new w-axis. And so now we have all of these increments of w marked off, and we could say this is 1w, 2w, 3w, 4w, etc. out toward the w axis. So this is w, and this is the vector x. And so now, instead of the x and y axes, which are defined in terms of I and j, we have the x and w axes, which are defined in terms of the vectors x and w. So we could almost call this the xw coordinate system instead of the xy coordinate system. We have a whole new coordinate system. And what we want to realize here is that we started with this vector 5, 3, and it was defined in terms of the standard basis vectors as 5i plus 3j. But if we look at our x and w axes, we can see that if we take 2 of x and then 1 of w, so if we go out 2 units along the vector x-axis, that gets us to this point right here. And then if we go up from that point 1 unit in the w direction, that would get us right here, and that is the tip of the vector 5, 3. So with 2 units of x and 1 unit of w, we can get out to 5, 3. So 5, 3 can not only be defined as 5i plus 3j, or just as 5, 3, but it can now also be defined as 2 times the vector x plus 1 times the vector w, or plus w. And it doesn't matter which way we go. If we had gone out 1 unit in the direction of w and then up 2 units in the direction of x, we would have ended up at the same point. So what we say then is, instead of this original vector v, we can say that the vector v expressed in terms of the new basis, so if we call this here, if we call this our new basis b, the vector v expressed in terms of b is given by 2 units of the x vector and 1 unit of the w vector. And so we can graph that same vector v in the new basis using this new definition of the vector v defined in the new basis b. What we want to realize now is that before, when we looked at how to get to the end of this purple vector, we just eyeballed the combination of the vector x and the vector w, and we were able to figure out just by looking at it that we needed 2 of the vector x and 1 of the vector w. But we can actually find this algebraically. If we know that we want to change our basis to this set of vectors here, then we can put these into a matrix as column vectors. So we can take the vector x and make that the first column vector, and then the vector w can be the second column vector, and we know that we want to get to the vector 5, 3, that vector v that we started with. So then we just say, in order to find the representation of the vector v, but in this new basis given by this matrix here, and that vector we know is 5, 3. We want to figure out how to get to 5, 3 in the new basis. So all we have to do then to solve for this vector defined in the new basis is augment the matrix with this solution vector 5, 3. So we say 2, 1, 1, 1, and then we augment with 5, 3, and then we just want to put this into reduced row echelon form. So let's go ahead and swap the first and second rows. So 1, 1, 3, and then 2, 1, 5. And then from here, we'll subtract 2 of the first row from the second row. So the first row will stay the same, 1, 1, 3. And then here, we'll get 2 minus 2 times 1 is 0. 1 minus 2 times 1 is a negative 1. And 5 minus 2 times 3 is a negative 1. Then we'll multiply through the second row by negative 1. So 1, 1, 3, and then 0, 1, 1. And then we'll go ahead and subtract 1 of the first row from the second row. So our second row will stay the same, 0, 1, 1. And then from the first row, we'll say 1 minus 0 is 1, 1 minus 1 is 0, and 3 minus 1 is 2. And so what this tells us is that because we get 2, 1 on the right-hand side here, that the vector v, the vector 5, 3, but expressed in the new basis b, given by this basis of the vector x and the vector w, is 2, 1. And we know that already because we found that we needed 2 of the vector x and 1 of the vector w, and that's what this is telling us. We need 2 of the vector x and 1 of the vector w. We can also convert the other way if we know Our basis is defined by x and w, and we know that the vector we're interested in is expressed in terms of x and w here, and we want to figure out what that vector is in terms of the standard basis, so we're going the other direction now, then we simply put in this 2, 1 vector for the vector v in the new basis, and we leave this vector, which is in the standard basis, as our unknown. So we would write it like this, 2, 1, 1, 1, and we put in our vector in terms of this different basis here, this xw basis, and then we leave open here this vector in terms of the standard basis. And so then if we do this matrix multiplication, what we see is that we get x, y is equal to, here we'll get 2 times 2 is 4, plus 1 times 1 is 1, and then we'll get 1 times 2 is 2, 1 times 1 is 1, and so we get here 5, 3, which is the 2, 1 vector expressed in terms of the standard basis. So in the standard basis, it's 5, 3. In this alternate xw basis, it's 2, 1, and we can convert back and forth between those two. Now keep in mind that there's one other useful thing that we can do with this transformation matrix. We call this a transformation matrix, or more specifically, a change of basis matrix, because it's helping us to change our base from the standard basis to this alternate basis. So this is our change of basis matrix. And what we realize is that we really have here this matrix A, we'll call it A, and then we have the vector v, but defined in the alternate basis, and then we have over here the vector v. If we multiply both sides of this by A inverse, so we'll say A inverse A, and then v in the alternate basis, and then A inverse times the vector v, what we have over here on the left is A inverse times A. That's the identity matrix I. So we just get I, and then V in B, and then A inverse, and then the vector V. And of course, multiplying by the identity matrix, multiplying by I, is like multiplying by 1. It doesn't have any effect. So we can simplify this left-hand side just by dropping the I, and then we can say V in the alternate basis is simply given by A inverse times the vector v. So what this equation is telling us is that if we have the vector v in the standard basis, so we were given the vector v 5, 3, we have that in the standard basis, we started with that. If we have this change of basis matrix, if we just find its inverse, then we can come up with an equation that lets us convert any vector from the standard basis to the alternate basis. So let's continue on with this example here, and let's say I take this change of basis matrix 2, 1, 1, 1, and I want to find its inverse. Well, to find the inverse, I could go ahead and augment that with the identity matrix. So we'll say 2, 1, 1, 1. We'll augment it with 1, 0, 0, 1. And now I need to get the left-hand side in reduced row echelon form. So let's switch the rows. We'll say 1, 1, 0, 1, and then 2, 1, 1, 0. Now let's take 2 of the first row away from the second row. So the first row will stay the same. And the second row will say 2 minus 2 times 1 is 0. 1 minus 2 times 1 is a negative 1. 1 minus 2 times 0 is 1. And 0 minus 2 times 1 is a negative 2. Then we'll multiply through this second row by negative 1. So we'll get 1, 1, 0, 1. And then 0, 1, negative 1, positive 2. And now we'll subtract the second row from the first row. So our second row will stay the same, 0, 1, negative 1, 2. And the first row will say 1 minus 0 is 1, 1 minus 1 is 0, 0 minus a negative 1 is a positive 1, and 1 minus 2 is a negative 1. So now 1, negative 1, negative 1, 2 is the inverse of this original matrix A. So if this is A, then we can say A inverse is equal to 1, negative 1, negative 1, 2. So that's our inverse matrix, and according to the math we did up here, we can say that we can find any vector v, we can find its definition in the alternate basis simply by multiplying this inverse matrix by any vector v that we want to. So let's say we wanted to find the representation of 5, 3 in the alternate basis, all we have to do is plug that in here and multiply this inverse matrix by that vector. So we get 1 times 5 is 5, -1 times 3 is a -3, 5 and a -3 is 2, and then -1 times 5 is a -5, 2 and 3 is 6, -5 and 6 is a +1. And so right away we know that the vector 5, 3 in the standard basis is represented by 2, 1 in this alternate basis defined by the vectors x and w.